Okay, let's try it then. So let me make this bigger. Okay, so we need a function. We can call this anything, but I'll call this factorial. And then let's think about what's going to happen when we run this function. So we're going to do like fact of 10, and then we expect to get 10 factorial. Do you guys all know what factorial is?
Like times all the way going down.
Yeah, so like 10 factorial is 10 times 9 times 8 all the way to times 1. Okay, so actually want this to print something.
Last time I went to Costco, there's this kid who was in 3rd grade, and he was like, he talked about all sorts of math, and he talked about factorial, and when he said that it was like 10 factorial is 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2.
That's
and
wrong.
Then, like,
I'm sorry.
And then when I was standing in line in school, a 5th grader asked my smart friend what was 10 factorial, and I tried to use his method, but like I got embarrassed.
Oh, okay. I'm sorry about that. Okay, so we want factorial to print a number. So instead we're going to do int factorial. Hopefully you guys learned this, that this int here means that this function is going to return an integer. How to do 10 factorial quickly, you haven't memorized. Okay, so what do we want this factorial to do? So 10 factorial is equal to 10 times 9 factorial. So we can just do exactly that. So we can return, x times factorial of x minus 1. So let's see how this works. Okay, so if you have something like this, and then we do factorial of 10, this x gets a 10. So we return 10 times whatever factorial of 9 is. All right, so then now we're calling factorial of 9. So now we're going to put a 9 here. So then this thing becomes 9 times factorial of 8. Yeah, so that's the next part. So this will multiply numbers going down by 1. The problem with multiplying numbers going down by 1 is if you don't stop multiplying numbers. So we need a base case. So what should our base case be? When should we stop? Okay, we can try 0. So if x equals 0, what should we do? Okay, return. Okay. We can try this. Oops. Okay, so let's try running this and see what happens. Okay, 1 second. All right. We can try running this. So if we run this, okay. Yeah. If we input 10, like here, then we get this number, which I think James showed us is right. Okay, why can't you use a ternary statement? We could use a ternary statement. So how do you think we should turn these 2 lines into a ternary statement? Does anyone have ideas on how to turn this into ternary? Yeah, Okay, so we can have something like this. So let's see what happens on this ternary statement. So if x is equal to 0, we return 1. Otherwise, we return this. So it's the exact same thing as these lines, except it's 8 times harder to read and not that much shorter. Okay. Are there any questions about this stuff? Why exactly 8? So you count the number of extra characters and then you divide it by the number of symbols. Can't you? Yes, you can use a for loop that counts down. In fact, for this example, that would be easier. But there are not that many examples of recursion that are pretty simple enough to like use what we've learned in the past 4 days. So yeah, you can use a for loop, but we're practicing using recursion. Okay. Okay, this is a bit harder. In fact, yes, that is true, but that's I did not make the schedule, so do not ask me. Okay. If we have time at the end, we can do other stuff. All right, let's try this. Yeah, you just need greedy here. So you're trying to make some number with quarters, dimes, nickels, and pennies. So for example, 68, you're going to print 7 because it's 2 quarters, a dime, a nickel, and 3 pennies, which add up to 7. Okay, I'll let you guys try this for like 5 minutes, and then I'll show you how to do it. Okay, I'll type a bit of code about this. So we need the function name. So it's going to return an integer. So int change index, and then do something. And then print change of 68. So let's think about it. So if we can use a quarter, is there ever a scenario where you wouldn't want to use a quarter to use the smallest number of coins possible? Like for example, let's say you have like 25 cents. It's always best to use a quarter, right? So we can check if there's enough to use a quarter, then use the quarter.
The person who makes this code is so greedy. The effort you have to use to like make this code is more than the effort the cashier has to give you the change.
Okay. You can copy and paste the bunch, so it's not that bad. Okay. So what does it mean to use a quarter? You used one more coin and however many coins it takes to do this. So for example, if you're trying to make change with like 36, x equals 36, you can use a quarter. So you use one more coin and then plus however many coins it takes to make 11 cents. Does this line make sense? Okay, so now let's say you can't use a quarter, like you only have 20 cents. What's the next best thing? Yeah, you could do that. Yeah, dime. So if you have enough for a dime, so let's say we're doing 20 cents again. So we have enough for a dime. So how many coins is a dime? It's just one. And then it's however many coins need to do this. So it's like, let's say you're making 20 cents, then it's like the cashier gives you a dime, and now they have to make 10 cents, which is x minus 10. Okay. And you can do a similar thing for the other things. Nickel and pennies. So, okay, question. Do we need a base case? Yeah, we do need a base case. So we can put it here. What should we return? So this base case means like, what do we do if we're making 0 cents? Yeah, thank you. If we're doing 0 cents, then we just don't return any coins. Okay, are there any questions about this stuff? Okay. What is a no dot dot dot? Okay, in that case, we can try this. And yeah, we get 7, like we expect. See out? No, okay. All right, so hopefully this works for like other amounts too. Oops. And yeah, so in theory, you would need 11,352 coins if you wanted to make this many cents. Okay. You can read the warning. Warning non-void function. Okay. Yes. It is not always agreed. It depends on the amount of coins you have. Brackets, if you wanted to check that by hand, you should go do that right now. And then you can tell me if you counted right. Okay, so earlier I saw there was someone who wanted to do this with vectors, which is a good idea. So if we had like a vector in coins with 25, 10, 5, and 1. So instead of using a lot of these if statements, we could do it differently. You could do like for each coin, do exactly what this is. So if x is greater than or equal to coins of I, then return 1 plus change of x minus coins of I. And then you don't need any of this. So this is cleaner. The warning was because it's not guaranteed that you return a number. For example, if you have a negative number, then it wouldn't return anything. But if you're trying to give someone a negative amount of change, I think you have bigger problems than that. Okay. So yeah, that's how you would do this problem. Okay. All right, let's try this now. This is a bit easier than this one. So let's try it by ourselves. make a function called power, which takes two numbers, a base and a power, and returns like base to the power. So for example, power of 2 comma 5 is 2 to the 5th, which is equal to 32. So let's try using recursion to do this. Yes, you do. Basically, you just want to turn the problem into a smaller problem. So for example, like if you have power of 2 and then 5, so instead of calculating 2 to the 5th directly, this is equal to 2 times power of 2 comma 4. So what you do is instead of calculating 2 to the 5th, you do something times a smaller thing of that same function. Yes, but power is bad and you shouldn't use it. Power x, y is really close. Yeah. It's slow. Admittedly, this is also slow, but okay. So, all right, I think someone pointed this out. But one observation is that if we have power of BP, this is equivalent to B times power of B and then P minus 1. Because you're multiplying BP times is the same as doing it once manually and then doing it, and then using a function to see how, like the number when you do it P minus 1 times. Yeah. So, well, first we need to return this instead of just like having it sit there. Brackets. Your code doesn't work. I'm sorry. Okay. So what's our base case going to be? Like, do we want this to go on forever? Because if we do like power of 2 and 5, it's going to do 2 times power of 2 to the 4th. Power of 2 to the 4th is going to do 2 times 2 cubed. And then this is going to go on for a very long time. So when should we stop, keep like continuing to recurse? Yeah, okay, so if p equals 0, you want to stop. So like, let's say you're checking power of 2 and 1. Yeah, correct. So what your code's going to do is 2 times power 2 0. So what like power of 2 0, when you go into here, this should just be 1. So you just want to check for this number, and if it's equal to 0, you return 1. And the reason why you turn 1 is because anything to the 0th is equal to 1, except for certain numbers. Okay, let's see what Victor did. So you did if you want to, yeah. So you would want to do return and then what you have. So return p equals 0 question mark, and then also you want to switch it because when p is equal to 0, the first one's going to be evaluated. So if p is 0, you do 1. Otherwise, you do b times power. All right, does anyone have questions about this? Sure, I can try running it. Okay, it works. All right, Ryan, so what you said is really close. The problem is that's never gonna stop running. So that's why you need this line, because when power gets really small, it should stop. Yeah. Okay. Let's try making this function. So it's fib of x returns the x Fibonacci number. So Fibonacci numbers are like 0 and then 1. And then to get the next number, you add the last two. So 1. So if you're here, you do 0 plus 1 equals 1. And then 1 plus 1 equals 2. Last two numbers are 1 and 2, so 3. Then 2 plus 3 is 5. Then 3 plus 5 is 8. Then 5 plus 8 is 13, etc. Yeah, that's a pretty good observation. Wouldn't iterative be fast? Yes, iterative would be faster, but like there are things you can't do without recursion. That's cool. You should try coding it now. Recursion is useful sometimes, but you won't be able to use it when it's actually needed if you can't like do the easier things with recursion. Okay, I'll let you guys try this for a bit, and then we'll go over how to do it. And then I think we'll have some time left over, so we can do fib of 13. Depends on what 13th Fibonacci number is. So 0 is the 0th one, 1 is the first one, this is the second one, this is the third one, this is the fourth one, this is the fifth one, this is the sixth one, seventh one. Yeah, so fib of 7 would give you 13. Yep, that's the like equation you want to use, although that's not really a function. Okay, cool. Okay, so I'll code a bit of it for now. Yeah, those are the numbers, but what if I wanted a very big number? Okay, so if we tried that, okay, what are we trying to get? So, Colby, do you know what the Fibonacci numbers are? Yes, okay, so we're just trying to get, fib of x is the x Fibonacci number. So for example, if you have like fib of 17, this is, sorry, not 17, 7, this is equal to 13. We want code that does this. So something useful someone said is fib of x is equal to fib of x minus 1 plus fib of x minus 2. So let's see how we can use this to solve this problem. Brackets, yeah, that does work. I'm gonna try to let more people try this by themselves. Class ends at 7:30. There's not much after this. So we can do some stuff you want to do. Okay, so let's try using this stuff on line 15.
Can you make a code that finds prime numbers?
Finds prime, yeah, sure, after this. Okay, so let's use this thing on line 15. So we're gonna return fib of x minus 1 plus fib of x minus 2. So let's see what this does for like fib of 7. So if x equals 7, it's gonna do fib of 6 plus fib of 5. So this is what the Fibonacci numbers actually do. So the 7th number is the sum of the 5th number and the 6th number. So that's what our code here does. Now we need, oh, okay. Yeah, okay, I would agree that would go on that particular subreddit. So we need some base cases for this, otherwise this is gonna go on forever. So what are like the small values of x we want this to stop on? If you want a hint, it's at the bottom. Okay, so we want, if we're looking for the 0th or the first one, we want to just return it. So if x equals to 0, we return 0. If x equals to 1, we return 1. And we do get 13. Okay, so I think brackets earlier sent a faster way of doing this, which is, yeah. So you can notice that it doesn't actually matter too much what x is, as long as it's less than 2. And in that case, we just return what it is. So if x is equal to 0, this is less than 2. So we return 0. If x is equal to 1, this is less than 2, and we return 1. So it does the same thing. Does the fib function itself find the placement in the fib? What do you mean by that question? Colby, this finds the like Fibonacci number at position x. So like this is the 6th one, this is the 7th one. Was that the question? Okay. And if we wanted to be like brackets and make this even shorter, how can we use ternary statements to do this instead? These two lines with one statement. Okay, so if we wanted to combine these, we can, not if. We want to return a number, regardless of what the number is. And we check if this is less than 2. So if this x number is less than 2, then we return the value of x. Otherwise, we return what's down here. So hopefully if we run this, it should also give 13, which it does.
Do you have to include CMath?
Why do you think we should include CMath?
Because mine didn't work.
If you include CMath, this does still work, but you don't need CMath. There's nothing in this code that requires CMath because we're just doing ternary statements, which are just part of C++ without CMath. And like this is a function we made ourselves. Run the code. I just ran the code, but I'll run it like 8 times if you want. And it's 13. You can probably go higher. And you get this number, which hopefully is the 20th Fibonacci number. Can't you do Fibonacci in log n? Yeah. You can do many things in log n. Can you make, okay, sure. Input n x. Int x int. Okay, is this better? Okay, let's hope this still works. Okay, cool. Is there a number you want me to try? $21. Okay, that looks like it worked. Okay. Why did I pick the smallest number? I think you know why. All right, we have like 15 minutes left. Okay, also if you Google recursion, Google tells you like, did you mean recursion, which is kind of funny. Okay, we have like 15 minutes. Is there anything you want me to do?
Can
Code.
you call Bob? Can you edit Bob?
Do you want me, okay, can someone send me current Bob code?
I'll send it in the chat.
Okay. Bob is overused. I agree. Okay, we'll do prime numbers first. Okay, I'm not gonna, okay. Liar, it should work. All right, yeah. Okay, what's a good way of doing this? Okay, we'll do prime numbers first. Okay, I'll do a very dumb way of doing this. So I'm gonna make a function that checks if a number is prime. Do stuff later. And then I'm just gonna go from int I equals 2 to like 100. And then if check prime of I, see out I and the. Oh my god. Okay, we'll do that after maybe.
I already copy and pasted Bob into the tab.
Yeah, I saw. We'll do that after. Someone wanted me to make a prime number generator. Okay, so how can we check if a number is prime? Can I code a sieve? If you can explain to these people what a sieve is in 10 minutes.
Can you find prime numbers by looking at trying to divide it by 2, and if it's like a float or something to detect that?
We have like modulo things to check.
Oh yeah.
Okay, anyway, so yeah, so we can just check. So if we have a number like 12, we can just check if it's divisible by like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then if it's not divisible by any of these, then that means it's prime. So for 12, this is wrong because 12 is divisible by 2, which means it's not prime. If we had something like 13, it's not divisible by any of these numbers. Okay, so let's try doing this with the for loop. We're going to start from 2, go until we're less than x. And then if we are divisible by 2, that means when you divide it, the remainder is going to be 0. So we can check if it's divisible, which means when you divide, the remainder is going to be 0. And if it is, then return false. So we return false. For example, if we had 12, we check 2, and it's divisible by 2. So we just return false because it's not true. But if we get all the way to the end, that means it's true. So we return true at the end. Okay, we can try this now. Okay, 2, 3, 5, 7, 11, 13, 17, etc. Which looks fine.
Wait, can I have the code? Just asking.
This code?
Yeah.
How do you want me to send it to you?
Just in the chat.
Okay, 1 second. Okay, all right. Does this link work?
Yeah.
Okay, cool.
Thank you.
All right, we still have 10 minutes. So I guess, okay. Slideshow. Here's the slideshow link. Okay, do you guys want me to code Bob, or do you want me to code a prime seed?
Can you call the Bob? So can you just add a story to Bob?
Add a story to Bob. What story would you like me to add to Bob? It looks like there's a lot of stuff about Bob already.
Not really. The output is really less. But anyways, code it.
Let me copy it first. Okay. Oh my god.
There's not much output.
Okay.
Let's see.
Okay. I don't know what else to add to Bob, so I guess we can do a seed instead. Okay, we're gonna do a prime seed. Okay, so let's say we want to go up to like 1,000. We can do a boolean of like is prime with 1,000 of them. Okay. I don't know what else to add to Bob, so I don't know what you guys want from that.
Just make like a if statement, like if Bob the favorite celebrity equals Mr. Beast, then see out Bob wants to be a YouTuber in later in life.
Okay. I can do that.
Asking what is a seed?
What is a seed?
Yeah.
Okay, I'm not gonna code it right now because of time, and it seems like more people want Bob. But basically, so if you're trying to find prime numbers, have you seen like this grid of numbers? It's like 1, 2. Actually, let me just find a grid of numbers. Give me a minute. I'm going to steal something from Google. If this thing loads. Okay, so let's say we have this list of numbers. Oops. Basically what you do is you like mark this number and then you cross out all of these numbers because none of these can be prime. And then you do that for like all the multiples of 2. And then you cross out the next number that you have, which is, or you circle this one, meaning it's prime. And then you cross out all the multiples. So like 9 is a multiple of 3, 12, 15, 18, 21, etc. And you keep doing this. So you circle the next number and then cross out all multiples. So yeah, eventually if you do this, you get all the primes.
Can you
So
make
it's pretty fast. I think more people want to see Bob's stuff.
oh
Sorry.
I think there's like a whole entire organization out there just trying to find the largest prime number.
Yes, there is. That's pretty cool. Maybe one day you can find some too.
Maybe.
And maybe you can make if Bob's favorite food equals is burger, then Print Bob will become very fat in later life.
Okay. Okay, we have string favorite food here. Is that ever used?
Wait, is 1 not considered a prime number?
No, people usually don't consider that a prime.
Oh, okay.
This, I don't think this will run.
Yes, hello.
Oh, well, okay, first off,
I already
Fine.
ran it on Replit before.
okay, never mind, sorry.
How did your Replit thing not die?
Okay,
Replit did not die.
this is wrong. And there's a missing something somewhere. I don't know why this is just here. Okay, this should run. Never mind. I don't know how your Replit ran this because it should not have ran.
Just do it on Replit.
I don't think that will work.
But I already ran on my Replit.
Yeah, okay, this does not work. It works up to like here.
Maybe you should try it on Replit.
Okay, it's,
Now can we like do some code for prime numbers?
okay, you can try this on Replit some other time then. Okay. We do not have much time. Okay, so we can need like a this. Okay, and then we're gonna go through all multiples of I. So we're gonna start from j equals I guess, and then j is less than 1,000. And then j plus equals I. So this goes through all multiples of I. And then if we do this, what we're gonna do is prime is equal to 0, meaning it's not prime. Actually, okay, is not prime. If we're here, it means this is not prime.
怎么在上课？课已经快上完哦。
Okay. And then we only want to do this if this is prime. So if it is not prime of I is equal to like 0, so it's false, then do whatever is in here. So first we set, okay, yeah, we just leave it like this. And then at the end, we can do for an I equals 2, I is less than or equal to 100 or 1000, I plus plus. If it is not prime of I is false. CLINO.
Can you test it?
Sure. Okay, so this is like really fast and it gives you a lot of friends.
Does this go on forever or
No, it stops at 1,000 because this stops at 1,000.
does that mean you can make it as big as you want?
You can make it pretty big, I think, but eventually it will be too slow. It's still pretty fast for big numbers though. My terminal does not render this many numbers. Is there a better way to find primes? Yeah, I think there are other sieves, like an Euler sieve and sublinear sieves.
And I have the code.
Yeah, sure. Okay, this is really bad code though.
I mean, at least it's something. And it's pretty cool, so
That's the right mentality. Okay, I sent it in the chat.
okay, thanks.
All right. It's pretty much 7:30. So if there are no more like questions or anything, I think we can finish the class. That's not every prime though. That's only some numbers. Yeah, but why would you want the largest one? You can have all of them. All right, bye-bye.
Bye, thank you.
Bye.
Bye, thank you.
Bye-bye.
Bye.